number 28. Okay. 28 says you are working on a research project in which you must control the direction of travel of electrons using deflection plates. You have devised an apparatus shown in the figure. The plates are of length ½ meter and are separated by a distance of 3 centimeters. Electrons are fired with an initial speed of 5×10⁶ meters per second into a uniform electric field from the left edge of the lower positive plate, aimed directly at the right edge of the upper negative plate. Therefore, if there is no electric field between the plates, the electron will follow the broken line in the figure. With an electric field existing between the plates, the electrons follow a curved path bending downward. You need to determine A, the range of angles over which the electron can leave the apparatus, and B, the electric field required to give the maximum possible deviation angle. So, all right, so let's go in and let's set up our picture. So there's our plates. And in the picture, what they give us, that this is the length of the plates, which they said was ½ meter. And then there's the separation between the plates. They said that was 3 centimeters. Okay. So make it into SI units. And then we have our negative charge is here at this bottom corner. And then in between the plates we have this uniform electric field. So this means the field line should be evenly spaced. Mine aren't coming out so great, but you know, you get the idea. Like this. And we're going to launch it with some initial velocity, and it said it was 5×10⁶ meters per second. Okay. And then we'll have some initial launch angle. We'll call it theta naught. All right, so if we want to go in and take a look at this, then and it said that it was initially aimed, at this other corner. So it should have been lower. I guess I need to fix it. It needed to be this way. There we go. Okay. So, and then what I can do is I can go in and pick out a coordinate system in which to work the problem. And so then my initial x coordinate is 0, the initial y coordinate is 0 because we're initially at the origin. We can go in and find our components of the initial velocity. I'll do a little component triangle like this. The other thing is that since we're aimed towards this particular corner, then we can get that angle, all right, just by the geometry of the plates that they specified in the problem. So let's do that. So then my initial angle will be this inverse tangent of the opposite side, the 3 centimeters, over the adjacent side, which is the ½ meter. So let's go ahead and calculate our initial angle, like so. Thank you. There we go. And then when we go and we write these down, that'll be VO cosine of theta naught. This will be VO sine of theta naught. And we know VO and theta naught, so we can get numeric values for those. I'll leave them for the moment. And so then the idea is that once this electron is inside this electric field, okay, like so, then, oh, I drew my plates wrong. These should be the negative plates. They're indicated in the diagram. This is the positive plate. Indicated. Yeah, I need to change the arrows. Go. The electric field points up. Now, what we can get is we can get our electric force. Okay. Now remember that the electric force on the charged particle inside the field is just Q times E. But since the charge is the electron and the electron is negatively charged, then tell me about the direction of the force compared to the direction of the field. So we know our electric field vector is going to point up. I don't happen to know the magnitude of the electric field vector. That's what we're going to find. And then the electric force is going to go which way? Up or down? It's a negative particle. So when you negate a vector, what happens to the direction?
It goes down the other way.
It reverses. So this is good. So then our electric force goes down. And so therefore the acceleration, since mass is only positive, then whichever way the net force is the direction of the acceleration. And so then we can go in and write down that our magnitude of the electric force is the charge on the electron, so that's E, the fundamental unit of charge, times whatever electric field we happen to have. And then with our Newton's second law, we'll have that the acceleration is the net force over the mass. And so this will be that our magnitude of the acceleration is going to be E times E over the mass of the electron, so the electron mass. And we know this charge, we know that mass. I mean, it's an electron. It's 9.11 10 to the minus 31 kilograms for the mass. The charge is negative, which is why the directions were reversed. Okay, and the value of the charge is 1.602 10 to the minus 19 coulombs, the fundamental unit of charge kind of thing. It's the little e. Okay, and so this is our acceleration. And so now what you'll notice is that, when the electron's going to move in through here, then, if there was no field, it'd hit this corner, but it's going to go in and arc over like this. Okay. And so then we have that our acceleration is going to point down. So the acceleration will only be in the negative y direction in this particular coordinate system. And so then when we come in and look, we get that, a y is going to be minus a, and that our ax is going to be 0. And so this is really good. Since the field is uniform, the force is uniform, the a is uniform, we get to do kinematics. And so then what we get is that with ax being 0, like we have here, then the only equation we really get, we get that, Vx is Vox is V average x, that the velocity in the x direction will be constant. And then for the positions, you get that the final x position is the initial x position plus Vox times the time. And then for our Ay being constant, then what we'll get is we get our standard set of kinematic equations, right? We get that Vx is Vox plus AX times the time. We're going to get that our X. These are Y's. VY, VOY, AY, because this is in the Y direction. And then we'll get that, Y is Y naught plus VOY times the time plus 1/2 AY times the time squared. And we get VY squared is VOY squared plus 2AY, and then Y minus Y naught. Okay? Now, when I look at this picture, if we want the electron to just leave the apparatus and go out this way, okay? If we want it to just make it out, then we want to determine what electric field value produces this motion. Then what we'll have is I know that my final X position, this is going to be plus L, and my final Y position will be 0. And so I can put that into here, and we can solve for the amount of time it takes the electron to transit the parallel plate. I can take that time, put it into the Y equation, and then try to come up with some expression for the electric field magnitude to produce that motion. Okay? So this is the part B of the example. That's probably the only one I'm going to do. So let's take a look at the positions, and then I'm probably going to take the times loaded into the Y equations and then see if I can't come up with an expression for the electric field magnitude. Okay? So let's look at these X equations. So X is X naught plus VOX times the time. Final X position will be L. The initial is 0. The VOX is VO cosine of theta naught for my X component times the time. And then what we can do is we can use this to get that the time will be L divided by VO cosine of theta naught. So there's the time it takes to go to the other side of the parallel plate. And then if I plug that into the Y equation, then my final Y position here is going to be 0. The initial Y position was also 0. The initial Y velocity was up, and it would be this VO sine of theta naught. The time that it took to transit would be this L over VO cosine of theta naught. My Y acceleration's in the negative direction, so it's minus, has a value of E times the electric field over the mass of the electron. And then my time is L over VO cosine theta naught squared, as I run out of room on the page. Okay, so let's clean this up. Those will cancel. This is just 0. And so I get sine of theta over cosine of theta, so I'll write that as tangent theta naught times L. And then this will be minus 1/2. This will be E over the mass of the electron. This will be L squared over VO squared cosine of theta naught squared with the square. And what I want to solve for is E. So we're looking pretty good. Move that to this side. Divide under and solve. So it'll be twice the mass of the electron over the charge of the electron. Then it's going to be this VO squared cosine squared theta naught over L squared times L. Tangent I'm going to rewrite as sine over cosine. So I can reduce. So this L squared will reduce with this L. This cosine squared will reduce with that cosine. Yep. And so I write this as the mass of the electron over the charge of the fundamental unit of charge. This will be VO squared over L. And then I get 2 cosine times sine. So that's sine of 2 theta. So I use this trig ID to simplify this one. Like that. And then we could plug things in and get an answer for the electric field. Okay.